I'm Ingo Stürmer, Chief Technology Officer at Volvo Autonomous Solutions. Today, I'll walk you through what it takes to run an autonomous transport mission in real-world operations. We will not just look at the autonomous truck, but at the entire productivity and hauling solution for quarries and mining applications. That includes vehicles, autonomy software, infrastructure, and autonomy operations, all working together as a one transport system. We call this autonomous transport system Autona Earth, and it's built for demanding and harsh operational environments. Here's what we will cover: how we digitally design and map a site, how the system senses and understands the environment, how the virtual driver decides what to do next, how those decisions are safely connected to the truck, how operations are run day to day, and how we test and validate before we even deploy. Let's dive in. Let's start with the foundation, the customer site model. Every customer site is unique. So first of all, we create a map. At some sites, hauling routes are stable and map updates are rare. At others, the routes change frequently as material is moved or dumping areas shift. In those environments, autonomy depends on being able to adapt quickly without compromising safety. In the example you are seeing here, the system automatically creates new road segments as its site changes. This is not just drawing lines on a map. It includes geometric feasibility, operational constraints, defined work zones. With the site and routes planned, we now can look at how the truck understands what is happening around it. So, how does the self-driving truck see or sense the world it's operating in? The answer is sensors. And a bit more technically, we call these different sensors modalities. Our autonomous mining truck uses modalities like radar, LiDAR, cameras, inertial measurement units, IMUs, and global navigation satellite systems, GNSS. Each sensor provides a unique perspective, enabling the autonomous vehicle to build a rich understanding of the world around it. As you can see, different sensors see the world in different ways. On the left is the world as the autonomous vehicle sees it. The small points arranged in radial lines around the autonomous vehicle are the LiDAR measurements. The larger purple and tan points to the front and the rear of the vehicle, respectively, are the radar measurements. On the right, we have the view from one of the fisheye cameras. Note how the wheel loader looks in the sensor data, visible towards the end of the clip. As the truck drives along its route, the sensors read the environment, sending the information to the autonomous driving software, enabling the virtual driver to understand where the truck is and how it is moving. Even in a mine, unexpected things can happen. A rock might fall from the bucket of a truck and block the way for the next one. If an obstruction appears on the road, the sensors pick up the obstacle and the truck stops. The operator in the control room can check through the cameras what has stopped the truck, and once the obstruction is gone, give the truck the command to start again. Through sensor fusion, all of the sensor data is aligned, and the autonomous driving software or virtual driver makes decisions on where to go. So we've explored how the virtual driver sees its surroundings and makes decisions. But those decisions don't mean much until they're turned into real action. Steering, braking, accelerating. That's what the AVCM, or Autonomous Vehicle Control Module, comes in. It's the essential link that translates decisions from the virtual driver into physical commands for the truck itself. Think of the AVCM as an adapter, much like the one you might need when traveling. It translates information from the autonomous driving system to the base truck and vice versa, sending information back and forth. Through the AVCM, the virtual driver directs the truck to brake, accelerate, turn, and so on. The base vehicle, in turn, sends information about, for example, wheel position and speed. Beyond translation, the AVCM is a critical building block in the overall safety architecture. It helps harmonize interfaces across different vehicles and supports multiple clients such as the autonomous driving system, teleoperation, emergency stop. Emergency stop is a fundamental safety function. E-stop buttons exist inside support vehicles, on the exterior of autonomous trucks, in the control room, and at locations around the site. When e-stop is activated, autonomous vehicles halt immediately. All vehicles, support assets, and site infrastructure are connected back to the control room, which brings us to the operations. Autonomous operations can look different at each site, but if we stay with the example we started with, a typical shift starts with the operator selecting which vehicles will participate in autonomous operations. They then create work orders defining where materials should be loaded, where it should be unloaded. Once that is set, autonomous traffic is enabled. After automated background checks, operation starts and vehicles leave their parking spots. At loading, operators manage the process both from the control room and from the wheel loader. A screen mounted in the wheel loader connects the loader operator to the site control system. The loader operator selects the loading spot and the autonomous vehicle is called in. The operator can monitor the loading process, including tonnage, and once complete, the truck is sent to its next destination. At unloading, a dozer operator selects an unloading spot on the map. The truck reverses into position, dumps the material, then moves forward in a controlled manner to confirm the load is fully released. This closed loop repeats continuously throughout the day, with the control room supervising the fleet and handling exceptions. So far, we've looked at planning, perception, vehicle integration, and daily operations. The final piece is how we prove that our autonomous transport solution, Autona Earth, is safe and reliable before it reaches a customer site. And that brings us to testing. We use a multi-layered approach to test and validate our autonomous transport solutions. Our principle is virtual first, real world ready. Most tests are conducted in simulations to achieve faster feedback loops, broad scenario coverage, cost-efficient scaling of verification work. At the core is a digital twin, a 3D replica of the customer site combined with vehicle models, the autonomous software stack, model sensors, and defined scenarios such as meeting and following other vehicles. This enables us to run large numbers of scenarios faster than real time. Then we progress to physical testing, including rigs and test tracks, to integrate hardware and software and confirm performance under real-world conditions. Results fed back to continuously improve both simulations and test setups. Finally, at the customer side, we perform real-world validation to confirm operational performance, safety behavior, and reliability in the actual operating environment. That brings us full circle, from mapping to sensing, from the virtual driver to vehicle control, and from daily operations to validation. All of that is Autona Earth, a complete ecosystem designed to run autonomous transport safely, reliably, and in the toughest environments with high productivity. The goal is simple: keep performance predictable and keep material moving safely.